and let us know. Thank you.
Awesome. Well, thanks for the introduction, Ann. And as Ann mentioned, I do like to hold questions until the end, and we should have ample time. If for some reason we do run short, the last slide will have my contact phone number and email, so feel free to reach out to me that way afterwards if we run out of time, or if you just have a question or a project you'd rather discuss offline and not in front of the entire audience, that's fine too. Just a reminder, for most of you probably know this is part of a series that we do, a monthly series that we do. And so some of you may have joined us in the past. If you have, welcome back. If you have not, welcome to the webinar series, and we sincerely hope you'll join us for more of these in the future. Today's webinar is Working with Nature, Low Impact Development, and Stormwater Quality Treatment with Compost-Based BMPs. I always like to give a little bit of an outline of how we'll move through the time together on the webinar. A lot of you are familiar with green infrastructure. I really like to just discuss that for a moment to lay the foundation of what we're going to be talking about the rest of the 45 minutes to an hour here, on how we're moving away from gray to green infrastructure, and really also low impact development, and how compost really fits into that equation. I'm not going to insult anybody's intelligence and tell them how well compost can work for vegetation establishment and plant health and sustainability. I think folks know that intuitively, but I am going to talk about how it is being used for volumetric reduction of stormwater as well as biofiltration applications. I talk about some of the various applications or best management practices of where we're using compost in these green infrastructure applications, really in stormwater applications, both for erosion and sediment control and post-construction applications. No pun intended, but I'm going to share what I consider some of the watershed research on the performance of these practices, and particularly in a couple of applications that really have application to a broader use of compost in a wide variety of green infrastructure applications, and how we're using that in engineering and design criteria for specific projects. I'm going to share some case studies with you. We'll have some time for a Q&A, and just a little bit of an early take-home message here, and I'll try to point these out, the take-home messages, as we move through the webinar. But one of them here is that although I'm going to share some science with you, it's not rocket science. We're really following natural principles and really trying to work with nature as opposed to against nature in order to manage and restore site hydrology and reduce stormwater. And you're going to see that throughout the presentation. But one of the things that we're really trying to focus on is preserving and rebuilding natural capital, and really enhancing ecosystem services to let nature do the work for us. And really moving forward as opposed to continually having to construct and manage using human-made constructs and materials, and you'll see that throughout. Just a little bit of a background. A lot of you have probably been exposed to numbers like this in the past. Recent study has showed that over 850 U.S. cities and municipalities have either outdated or under-designed stormwater management infrastructure. That's not the only reason, but it is one of the leading reasons why 3/4 of all Americans live near a polluted water body, according to the U.S. EPA. And if we were to get on their website for their TMDL designated water bodies or impaired water body list, we're approaching nearly 50,000 water body segments now for a single or multiple pollutants. A somewhat dated study has said that what we pay as a society to clean up our surface water bodies due to poor stormwater management is about $44 billion per year. This is a slide I commonly use in all my presentations, but and something a variation of this you've probably all been exposed to at some point. But basically what this is showing is, as we change our land use patterns from natural systems that have a high degree of natural capital and ecosystem services are really working with us or for us, as you see in the left here, in these natural systems, what happens is, as we move towards the right, as we change our land use patterns, that has a severe effect on site hydrology as well as watershed hydrology. And what the color coordination is showing you here is that with more and more impervious surface and less natural systems like biomass, vegetation, organic matter in the soils, those types of things, we not only increase our surface roughness, but what I've included here too is we're also increasing our pollutant load. Most of you are aware that there's a direct correlation between runoff volume or stormwater volume and pollutant load. So pollutant concentration times the volume of stormwater equals your pollutant load. So it's really more appropriate to talk about pollutant loads, not necessarily concentrations, because we're talking about the amount of pollutants or pollution that is leaving a site or getting into a water body. And that is really the chief concern, I think, for most watershed professionals working in this area. And of course, the higher the amount of a pollutant or pollutants leaving a site, the more potentially is getting into a water body, leading to increased water quality impairment. So you can make that long story short and show that and say that the more impervious surface in a watershed, generally speaking, the more polluted or impaired those water bodies will be in that watershed. Now, we know under natural systems where we have natural hydrology working with us in the form of evaporation, transpiration, infiltration, subsurface or interflow, natural biofiltration mechanisms, we actually have very minimal to no pollution, which you see to the left here. There's another way to look at this, and this is one of the key take-home messages I mentioned in the outline, and that is you're looking at the very same graphic, but as you can see in the urban environment where we have a lot more runoff, where I've also mentioned we have a lot more pollutant loading as well, we have to have real infrastructure to handle not only that increased runoff that comes from impervious surfaces and land development, but also the ability to treat the increased pollutants as well that we find in that stormwater. So we have to pay in real dollar terms, whether it's in infrastructure provided by our municipalities, or treatment by our industries and our businesses, or even lost value in real estate in our neighborhoods and in our homes and everywhere where we live, work, and play. So those are real dollar terms, and that really is the idea of gray infrastructure. More and more impervious surface, more and more population, more and more land development, more and more gray infrastructure, costs more and more money to implement, maintain, and to keep up. Well, nature, as far as we can implement those systems into the urban environment, is actually doing that for free. So that's the idea of green infrastructure, is to put these natural systems into the urban environment, not only to enhance these natural systems, because generally people like to be around these natural systems more, but the idea is that it can bring that red down, not only in stormwater, but actually being in the red, monetarily speaking. And we can take advantage of those free services of nature that nature provides. And I'm going to share with you a case study of how we can actually quantify this. When we talk about polluted water bodies, particularly due to pollutants in runoff that are getting into our surface water bodies, there are some key pollutants that are that always kind of crop up. So there's obviously almost an infinitesimal amount of pollutants that could get into a water body, but as far as stormwater runoff is concerned, honestly, there's actually not that many. So some of the leading ones I have in bullet form here: coliform bacteria, metals. This is copper, cadmium, chromium, nickel, lead, and zinc. These are all byproducts of either roofing systems or the transportation industry that we typically see coming from rooftops or parking lots, highways, streetways, that type of thing. Nutrients, really just macronutrients of nitrogen and phosphorus that can lead to algae blooms and eutrophication and low dissolved oxygen levels. Sediments, of course, whether you're talking about construction activity or even in the post-construction world. And it's really the fine sediments, clay and fine silts, that lead to higher turbidity and suspended solids. and then of course hydrocarbons, motor oil, diesel fuel, and really to a much lesser extent gasoline. And you can see in parentheses here the number of stream segments listed on the US EPA's TMDL impaired water body list that have been affected or are listed as impaired for each one of these pollutants. Where are some of these coming from? I've mentioned some of this already. Parking lots, highways, streets, and rooftops are really the leading sources for metals. The first two there are also the leading sources for oil and grease as well. Golf courses and lawns are some of the leading sources of nitrogen and phosphorus runoff. Pet parks are actually the leading source of fecal coliform in runoff coming from the urban environment. Who cares the most about this? Well, we do have stormwater permits where there are effluent limitation guidelines in effect or being implemented for various industries, for municipal separate storm sewer system permit holders, really municipalities of certain population sizes across the country, and construction activities have to have a stormwater permit if land disturbance is 1 acre or greater. And there's been discussion about effluent limitation guidelines for construction activities as well. In fact, there are limited areas where that is ongoing already. Priority areas that we're trying to protect, anywhere where there's fish-bearing waters that we use in commercial fishing and that we're eating, like trout and salmon are the top ones. Anywhere where there's a known endangered species or water bodies have already been shown or known to be eutrophic, probably because there's been a lot of nitrogen and or phosphorus getting into those water bodies. Anywhere where we're actually touching the water and recreating, beaches, swimming areas, where we're boating, those are priority areas. And of course, if it's already listed as a TMDL designated area or water body, that would be a priority area as well. These terms, green infrastructure and low impact development, even restoration, hydrology, or sustainable stormwater management all get thrown around quite a bit in this industry and in this application. LID, or low impact development, green infrastructure, are probably the terms of most frequent use. For all intents and purposes, they are pretty much the same thing. Green infrastructure is really the phrase that the US EPA has coined, and so it's getting a lot more traction these days. It's really their low impact development program. There is one noted difference, I think, in the strict definition of green infrastructure, and that is green infrastructure is not only the implementation of these practices into a site or a watershed, but it actually goes one step further, and then it gets into collection and reuse of rainwater and stormwater, where low impact development hasn't really, at least historically, gotten into that collection and reuse. Strict definition for LID is that the post-development hydrology should mimic the pre-developed or the natural site condition. And you can see here a list of bullet points of really the key tenets for these programs, no matter which one you're kind of linking yourself with, whether it's reducing runoff volume, reducing those peak runoff rates during storm events, trying to reduce pollutant loading, trying to reduce off-site flooding, trying to minimize or prevent combined sewer overflows in urban environments. And really the idea behind both of these is to protect or improve water quality, protect or improve wildlife habitat and biological diversity, both in the water, surface water bodies, and on land. And of course, these programs also generally improve land aesthetics, which almost always leads to improvement of real estate and land values. I realize that few of us actually work on a watershed scale, unless that's probably part of your title, working with a state agency or a federal agency, or potentially a nonprofit. Most of us actually work on a site scale. That's one of the reasons why I'm showing you this slide. You'll notice that the percentages here on how hydrology and stormwater are managed in the natural site are very much the same as what I showed you on the watershed scale, very similar. But there's another reason why I'm showing this to you as well, and this is where compost begins to fit into the equation. You'll notice that you see a layer of organic matter and topsoil here in the natural environment. With compost, we're actually trying to manage for that. So unfortunately, one of the first things that happens during land development, we may inherit a natural site like this, and we'll clear off the vegetation, scrape off the organic matter and topsoil down to the subsoil, and put seed and fertilizer and silt fence down and call it good. Well, something that's taken potentially thousands or millions of years to generate, we take it away in minutes. Okay, and the idea is that with compost, we can actually replace a lot of this organic matter and really these hydrologic values as quickly as we took them away. Now, don't mistake, I'm not advocating for mass clearing and grading and simply putting down mass amounts of compost. In fact, that actually goes against what green infrastructure is all about, as well as sustainable site portions in LEED, as well as the Sustainable Sites Initiative as well, where you try to protect and preserve as much of the natural site as you can. But this is land development, and obviously there would be no land development if we were protecting and preserving all of it. So there will be areas where we need to retrofit in some of these natural systems. And from a hydrologic standpoint, compost can do a very good job of replacing these numbers, and then providing the very really a jump start and providing the foundation or the framework to then allow vegetation establishment, sustainability, and if managed correctly, ecological succession, where we can get a lot of the above and below ground interactions like that are depicted here in the slide. There's also something else going on here too, and if you look at the water that is detained or infiltrated moving down through the organic matter and topsoil layer, whether it winds up as subsurface or interflow or goes down deeper and recharges our groundwaters, either way they either recharge our surface water or our groundwaters. But when rainfall or infiltration water, stormwater, moves through that soil profile and percolates through, it actually gets naturally filtered in that process, really biologically filtered. And that's something that we're also mimicking with compost technology and applications, and we'll talk more about that in a moment. So this is going to be one of your key take-home messages here. If you're new to this, this is a very important aspect. So the type of compost we're using in all of these applications, there's really two types. And I'm going to share with you all the different applications in a moment, but there's only two types of compost we're using. They're depicted here. One is what we call filter media or biofiltration media, and that's on your left. And the other one is what we use for growing media. It's also what we use for erosion control and slope stabilization. That's on your right. Okay, the one on your left designed for optimum filtration as well as hydraulic flow through. We want water to move through these materials. We don't want it to create a dam and create a lot of retention time. That's not what we're looking for here. Growing media is designed for maximum absorption of rainfall as well as optimum plant growth. So you can look at the material on your left and see that it's probably not going to do a great job of establishing vegetation, but the one on the right will. We're also designing for surface roughness with the one on the right as well, which in and of itself is a best management practice. So if you're thinking to yourself right now, wow, neither one of these look like compost to me, or that I've been either using in these applications or I use in my garden or as part of a soil blend, then ding, 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 you are correct. And in fact, that compost, while it is maybe high quality compost for those applications or other applications, it is not considered a high quality compost for these applications. And so it's critically important to get the right particle size media and material for these applications, or you will get a much reduced performance level in really all of these applications. And it sounds a little funny, I think, when we talk about compost this way, but a lot of research has happened and been published determining the optimum particle size distribution of these media in these applications. I'm going to share some of the research here with you momentarily. This is a list of all the best management practices, the ones on your left, and these all use compost either in whole or in part. The ones on your left are for construction activity, stormwater management. The ones on your right are for post-construction. I've highlighted the ones in red that use that growing media, so that's the one picture to the right. So these are all mostly vegetative establishment practices. We're going to talk. We're going to talk more specifically about these here and some of the research behind it. But just a little bit of a refresher. You've seen this slide already, but the applications we're going to be talking about here are really designed to mimic this organic matter and topsoil layer that you see here in this natural system. So you see some visuals here of a lot of the different applications, from erosion control and slope stabilization to green roof applications, bioretention systems, reducing runoff around a stormwater pond, and even vegetating riprap along a riverbank there. When we use compost in these surface applications, they're really designed to do 4 key things. Number one is we're generally covering a bare soil surface to start with, so it's preventing that first stage of erosion, which is splash erosion or soil particles dislodgement. Really anything that physically covers a soil surface can do this quite well. This is not unique to the compost blanket, but it does a great job of doing it. Number 2 and number 3 and number 4 really are where the great benefits come in here, and that is these things are natural mega sponges, and I'm going to share some data with you here in a minute, but they actually have the ability to hold an immense amount of rainfall, and if we're holding it there at the surface, it allows it to naturally infiltrate down below. It allows it to restore natural evaporation patterns back up into the atmosphere, and of course make it become plant available as well. It's the smaller particles that actually do this function. It's the larger particles that do number 3. So at some point, if rain continues, you've reached field capacity, and now you get surface runoff, and we want to keep that sheet flow as slow as possible, because the faster it gets, the more erosive it gets, the more destructive it becomes once it leaves the site or hits a channel or a riverbank, and also it carries with it more pollutants. If we can keep it slow, not only is it less destructive and erosive, but we also give it the ability to find pockets of infiltration too as it's moving down the flow path. It's the larger particles that do this, so we're actually designing for surface roughness, which is actually a design element in both low impact development and in erosion control design. Number 4, optimum vegetation growth, and of course if you have a high quality compost, I think we all know that it's good for vegetation establishment and sustainability. This is a research project published in the Journal of Soil and Water Conservation. It was done at the University of Georgia, comparing compost blankets to straw mulch, and also evaluating particle size distribution as well. But one of the things that we found was that the compost blanket on average was absorbing about 84% of a 4-inch rain event. Now, no pun intended, but let that sink in for a minute. Okay, so what that means is it's absorbing a high percentage of the rainfall from a high intensity and accumulation event. So under normal rain events, probably 90 to 95% of the storms that we would encounter of a 1/4 inch, a 1/2 inch, 1 inch, even 1.5 inches, it's absorbing either all or nearly all that rainfall. And if it's absorbing all the rainfall, or nearly all of it, basically there's no runoff. Okay, and if there's no runoff, there's no erosion. If there's no runoff, there's no transport of pollutants. If there's no runoff, there's no water or pollutants leaving the site, or at least the application where you've put this. That can have profound effects not only on the idea of low impact development, but also having to make not only our gray infrastructure work less hard or less needed. You can meet low impact development ordinances. You can also reduce the size of a lot of these, not only gray infrastructure, but even green infrastructure practices, ponds, bioretention systems, containment systems, rain gardens. Really, if you can reduce the volume like this is showing, it really can have a profound impact on everything else on the site and even off-site. These are 4 different published studies, 2 from the University of Georgia, 1 from the University of Connecticut, and 1 from Iowa State University, all showing drastic runoff volume reduction when using a compost blanket, from nearly 50% to 90% volumetric reduction. Similar results seen in reducing the peak flow rate. Again, it's the coarser, larger particles that help with this function, but anywhere from 36% to nearly 80% peak flow rate reduction. This is a compilation of studies looking at the references on the left-hand side of the table, starting at the top. This is from Texas A&M University, 2 from the University of Georgia, 1 from Iowa State University, and the pollutants that we're looking at here, you can see across the top total nitrogen, nitrate, nitrogen total, and soluble phosphorus and total sediment. So what this graphic or this table is showing you from all these studies is the percent pollutant load reduction of a compost blanket compared to the way that we normally establish vegetation on sites. Okay, so the compost blanket, each one of these studies looked at a compost blanket and compared it to what I have in parentheses under each one of the references. So seed and fertilizer, hydromulch, seed and topsoil. So just to give you an idea of what you're looking at here, because I know it's kind of a lot of data, but if we look at the first one, Mukhtar et al., 2004, total nitrogen, a compost blanket reduced total nitrogen by 88% compared to seed and fertilizer in that research experiment. So pretty profound. It's pretty interesting that we see some pretty consistent numbers across each one of these studies. There have been quite a few of these that have been conducted since then that are showing similar information, and there's really two reasons why we see this. Number one is something that I've been hitting home quite a bit, and that is these things reduce runoff volume to such a degree there's very little pollutant load or lower pollutant loads leaving these test plots or leaving these sites where they're applied. But it's also the form of the nutrients as well. So when we're dealing with high quality compost, the form of the nutrients is in the organic form as opposed to inorganic or mineral form. And when it's in organic form, it is much less mobile in runoff conditions, so it's much less likely to be transported and leave the area or leave the site getting into sensitive water bodies. Runoff curve numbers gets into the design, moves from the research into the design element a little bit here. I know many of you probably don't use runoff curve numbers, but some of you probably do. They're a key aspect in this discussion because not only, one, if you do use them, but two, it helps exemplify how this information is being used and how important it actually can be. So runoff curve numbers originally created by the Soil Conservation Service, now the NRCS, for 4 distinct hydrologic soil groups, A, B, C, and D, of various soil vegetative complexes and their ability to reduce runoff or not. Basically what you're looking at are book values for various watershed surfaces that they have determined and their associated curve number. So what you see here is there's no such thing as a curve number of 99 or 100. 98 is generally as high as it gets, which you see here in the table. But basically what a curve number is, in pretty simple terms, is the percentage of rainfall that hits that surface that winds up as stormwater runoff. So you can see as we go from top to bottom, these are more impervious surfaces going to more porous and pervious systems and natural systems that are more absorptive and increase infiltration and storage capacity as well of rainwater and both from soil and vegetative complex. So if you compare each one of these and you look at the curve number, basically as an example, parking lot, driveway, and roof has a curve number of 98. That basically means that 98% of the rain that hits that surface will wind up as runoff. So just about all of the rainfall that hits it will wind up as runoff, and we all know that intuitively as well. The more vegetation and more natural systems we see, the more that actually gets reduced. Well, from looking at a compilation of the studies that I've shared with you, a vegetative compost blanket has a runoff curve numbers of 55. You can see how that kind of fits in with some of these natural systems. So why do we care about that? Well, we care about that for a couple of reasons. One, now we have something that we can actually retrofit back into these systems to get a lower curve number or an average curve number across a site or a watershed. But I think even more importantly, some of us have low-impact development ordinances based off of curve numbers that we need to meet, and I think more and more we're seeing this. But I think even more importantly, runoff curve numbers are actually used to predict or design stormwater ponds, bioretention systems and rain gardens, stormwater vaults and containment systems, because they're all based on volume. So if we can reduce the volume flowing to those systems, and it's really based off of the average of the composite curve number from the drainage area, if we can reduce those curve numbers, that means there's less stormwater going to those systems, and that means we can reduce their size. And if you're talking about a suburban or an urban type environment where we can reduce an underground vault, or we can reduce the size of a stormwater pond, wow, wouldn't the engineer or the landowner or the developer be extremely excited to be able to reduce the size of that stormwater pond so they can put something of higher and better value or use on that land, particularly in an urban environment where that can be critical. Let's quantify how this sort of plays out here and how we're using the services of nature and free ecosystem services to actually reduce in real dollar terms what we're spending in comparing a green versus a gray infrastructure practice. So let's look at a compost blanket versus an impervious surface. Our design area is 10 acres in size, and our design storm is 3 inches in a 24-hour period. Pretty typical design storm that a lot of folks use around the country. If we look at the stormwater generated from these two surfaces, we have the compost blanket will generate about 54,000 gallons of water, while the impervious surface will generate just over 750,000 gallons of water. Okay, that's a 1,400% increase. Okay, not only is that important to know, wow, the drastic increase, but in real world terms, something actually has to be done. You can't just say, wow, that stinks, that's a lot of extra runoff that we have to worry about. It actually has to go into some sort of green or gray infrastructure to handle it. So let's look at, we're working with gray infrastructure here so we can really sort of monetize and financially evaluate what that really means in dollar terms. Option number one, there's generally two options. Option number one is to build some sort of containment system. The cheapest option by far is to build a stormwater pond, not some sort of vault or underground storage system, which can be extremely expensive. Let's assume a real estate value of about $50,000 per acre. Average stormwater pond design and construction cost is about $1 per gallon of storage. Typical stormwater pond is about 4 feet deep, so based on the amount of stormwater volume and the depth, that's going to take about a half an acre stormwater pond. Now we just lost about a half an acre in valuable, usable real estate in perpetuity. And as that real estate value increases, which we hope it will, that number actually increases to $25,000. Stormwater pond design and construction cost is just under $700,000. So we add both of those up, and we're just over $722,000. Realize that this is just the upfront cost. There's no maintenance or upkeep here. Okay. Option number two, we can't build a pond or a storage system. We have to discharge it all off-site into the gray infrastructure grid, okay, into storm inlets and underground combined sewer systems or whatever we have in that particular urban environment. Water conveyance cost is about 26 cents per gallon. Water treatment energy cost is about 2 kilowatt hours per 1,000 gallons of water. An average energy cost is about 13 cents per kilowatt hour. Realize that can range quite a bit depending on where you are. Carbon emission is about 2 pounds of carbon dioxide per kilowatt hour. So let's add that up. We're paying about $181 in water conveyance per year, about just under $100 per year in energy to treat that water, and about 1,400 pounds of carbon emissions, carbon dioxide equivalent emissions generated from the energy expended to treat it and convey it and treat it. So realize that this is an annually occurring cost or fee, what we're looking at here. So at first glance this looks like the cheaper option, but realize this is an annually occurring fee. So after several years actually this becomes the more expensive option. All right, let's transition a little bit here and talk about filter media or biofiltration media. I'm going to give you a little bit of a graphic of what a lot of these look like, from sediment control to check dam, inlet protection, biofiltration applications at big box store parking lots. We include vegetation in some of these systems as well, particularly if they're permanent or post-construction. I've highlighted in red here are all the ones that use the filtration or biofiltration media, and most of these really use the Sock system as well, which filtrexx has created and patented. You've seen this slide already a couple times, and this is really just a refresher that what we're mimicking here is that arrow that's pointing downward. So when rainfall or stormwater infiltrates and then percolates through that organic matter and topsoil, it actually gets naturally filtered in that process. We're actually mimicking that characteristic, but we're doing it above ground. So we don't have to have the benefit of a depression and engineered soils in a bioretention system or a rain garden that can take a considerable amount of footprint. To do that, we're actually putting this above ground. So we know we're going to have some surface runoff, particularly in a developed landscape or watershed where those percentages are going to be greater, but we can get that biofiltration characteristic or aspect in the flow path before it gets into that surface water body. It's been said that the compost filter sock really is a three-way biofiltration system or technology or mechanism. The first one is really not all that unique. There's a physical mechanism here, and it does this in two ways. Through a variety of particle sizes of the compost media inside, we create pore spaces and openings to allow water to passively move through, but we're trapping various sizes of sediment. Also, because we're temporarily restricting flow, we're actually getting some sediment deposition as well. So we're getting some filtration as well as deposition as well. Those characteristics are not necessarily unique, but it is important that the right particle sizes are used to get that benefit and to get that performance. What is unique are these next two bullet points, and that is the chemical component. So we're using organic matter. We also have some degree of humus as well, and there's a lot of studies that have shown that not only organic matter but humus as well and soil systems can absorb or sorb various types of pollutants in soil solutions and in these environments. We're just putting these in the water environment, stormwater environment now. We've actually been able to quantify that. An example of that is organic matter sorbing or adsorbing ammonium nitrogen and some metals. I'm going to share some information with you momentarily on this. Biologically speaking, we get a benefit from this as well. So we know that there's a high degree not only of population but also diversity of beneficial bacteria and fungi in these compost systems, even a much higher degree than natural soil systems, believe it or not. And that's one of the reasons why compost has been widely used historically and promoted by the U.S. EPA for bioremediation and ecosystem restoration applications. So these pollutants that we're trapping in these systems, we're actually getting a bit of a in situ bioremediation going on within the sock. Different bacteria that we find in the composting process, those are typically thermophilic bacteria, but beneficial bacteria, none the same. There's also a fourth component I could put on here too, and that would be phytoremediation, or the ability of plants to uptake some of the pollutants that we're trapping in these systems up into their biomass, and that's really a lot of what bioretention and rain garden and constructed wetland systems are all about as well. As I mentioned, particle sizes are a key thing here, and this is a graphic that really kind of shows this. What you're looking at here, if you look at the bottom and particle size, this is in inches. So if we go from basically a 1/4 inch to 2 inches in size for the majority of the media, what happens is the flow-through rate or the hydraulic movement of water actually increases through these systems, but the filtration ability goes down. Okay, more water goes through, but also the pollutants as well. If we get finer media, the flow-through rate, the filtration ability increases, as you see, but so does the flow-through rate. We're basically creating a dam, so we're not only restricting flow greatly, but we're just basically blocking everything. This is exactly how air filters in your HVAC system are designed and created, as well as in air filters in your automobile or a water filter in your fridge or your sink or your pool. They design for apertures or pore spaces, and the bigger those are, the faster air or water moves through, and the less capturability they have, and the smaller those apertures are, the more restrictive they are in flow, but they generally trap more stuff, whether it's in the air or the water. Same principle at work here. So once you think about that, and you think about compost, and you think about the type of compost that you've been using in your garden or agricultural applications, now you begin to realize, okay, that stuff really can actually lead to big problems if I use that type of media. And the prime example here is the inlet protection sock you see in the upper right-hand corner. We're dealing with an impervious surface. There's a reason why that storm drain is there. We still want stormwater to get in there, but we want to trap some of the particulates and soluble pollutants that are getting into that storm drain without restricting flow, without rediverting it or ponding it. So you can see why coarse media, something with a high hydraulic flow through rate, is very important in a situation like that, because the worst case scenario here is that we pond water, divert water, and create a hydroplaning effect for oncoming vehicles or traffic, and it's either somebody gets hurt or there's destruction of property. Some research here I wanted to share with you. This is from San Diego State University using a ASTM test method D6459 for road erosion control products on the performance of filter socks, silt fence, and straw wattles. You can see the removal efficiencies here from 77% to 72 to 59%. This is a study done at the University of Georgia. This is published in the Journal of Soil and Water Conservation, looking at two different sizes of compost filter sock, an 8-inch diameter and a 12-inch, compared to a wood chip filter berm and a straw bale. Couple key take-home messages from this study. We found that Compost Sock is outperforming these other devices, as you see here, but we also found that you don't get more filtration from a larger sock. The only reason to really go to a larger sock is to handle more runoff or greater drainage area or longer slopes, not necessarily to get better water quality. You'll see this actually reflected in our design specifications, and you should see that, by the way, in whatever design specs you use for these or similar type devices. Study also published in the Journal of Soil and Water Conservation, research done at the USDA Ag Research Service at their research headquarters outside of Washington, D.C., comparing both the silt fence and the filter sock for suspended solids and turbidity. And you can see the removal efficiencies and reductions here. Something really interesting is these studies I've shared with you across 3 different studies from 3 different regions using 3 different soil types, meaning 3 different sediment types and concentrations and loads and experimental designs, but they're all showing roughly around 80% removal efficiency for the filter sock. So this is 78, this one was just over 80, and this one was 77. Pretty unique and pretty remarkable, actually, the consistency of the performance that we see across these studies. There's another one about 80% for TSS, right on the mark. This is a study that was done also by the ARS, published jointly in the Journal of Environmental Quality and Journal of Soil and Water Conservation. They wanted to now look at the compost filter sock as a true biofiltration mechanism, not just a sediment control device, which is how it was originally created and designed at Filtrex. So what you're looking at is the pollutant removal efficiencies for soluble pollutants for each one of these listed pollutants and the removal efficiencies there in the table. So this is important in low impact development and post construction, because we know where we have soil stabilization, whether it's from impervious surfaces or vegetation. Studies have shown that really up to 80% or roughly 80% of the total pollutant load is in the soluble fraction. It's not attached to sediment or particulates like we have in land disturbance and construction activity. So we have to have devices that can remove or absorb or take out these soluble pollutants. The sediment-bound ones as well. It needs to do both, but we already know that the compost filter sock practice and technology does a great job of doing that. Particulate and sediment, not only those fractions, but also pollutants attached to those if you're getting that sediment. So I want to share with you quickly a study that we collaborated with the ARS on. Some of my co-conspirators here at the ARS. We looked at developing a natural additive to the compost filter sock to specifically target nitrogen and phosphorus, bacteria, metals, and hydrocarbons. So the first one here is the very fine sediment, the sediments that lead to high suspended solids and turbidity that really stay in suspension, not like clays or large silts that really fall out and just don't really lead to turbidity or suspended solids. You can see the particle size classes here, but what we found is that we could remove roughly 60% of the clay sediment particulate and about 75% of the silt particulate. So we didn't need to do that by high residence or flow restriction characteristics. We could do that using a biofilter as well. We didn't have to build a sediment or a stormwater pond to get that benefit. Phosphorus, we found that we could remove some phosphorus with the sock alone, but we get very high removal efficiencies with our Phoslox or Neutralox additive, over 90%. Similar with nitrogen removal, we found that by adding our Neutralox additive specifically designed to target nitrogen, soluble nitrogen and runoff, we could remove close to 35% of ammonium nitrogen and about a quarter of nitrate nitrogen. Bacteria, we found very high removal efficiencies for total coliform and E. coli, really in the 99th percentile for removal of these classes of bacteria. Metals, I got a lot of data on the slide, so let me walk you through it. I got 6 different metals here going across the top of the table: cadmium, chromium, copper, nickel, lead, and zinc. I separated the data into 2 different forms, which I've highlighted in red text. Okay. The total removal efficiency for the pollutants is listed at the bottom, starting with 73%, 47, 70. But above that, I've broken it into the soluble fraction and the sediment or particulate bound fraction, because it's very important, I think, to know how these technologies or these practices work to remove the soluble fraction of these pollutants, particularly metals. We know that anything that's attached to sediment or particulate, we're probably going to get roughly 80% removal efficiency for that, as we've shown in some of the other studies. But it's that soluble bound fraction and using it as a true biofilter that we really want to know what's going on. So those values are the top row, starting with 72% for cadmium, 29 for chromium, 70 for copper. The sediment bound fraction is the one in the middle there, starting with 77%. And then finally, hydrocarbons. We found that with our Petrolox additive, we can remove in the 99th percentile of both oil and diesel fuel. Getting close to 60% for gasoline, but honestly, this is not something that we hear much about. Gasoline evaporates nearly as quickly as it hits the ground unless you have a spill actually during a runoff event or into a runoff event, which doesn't happen that often. I want to share with you quickly before we run out of time here a couple of case studies. We did a project with the city of Chattanooga. This is a MS4. They're out of compliance with their MS4 stormwater permit. The picture shows a 5.5 acre parking lot where they store and service a lot of their city vehicles, and they were out of compliance with stormwater coming off of this site back in February of 2007 for chemical oxygen demand, suspended solids, and oil and grease. You can see the concentrations there in the table. The main outfall for this property is the pipe you see here in the second photograph, and your property line is where you see that fence. So once the stormwater passes that fence line, it really needs to be in compliant, and the state does periodic stormwater testing at this location. So we came in with a retrofit with a vegetated sock system and a compost biofiltration baffle, which you see in the photograph. And at the very next stormwater sampling and analysis in June of 2007, not only got them back in compliance, but we kept them in compliance. I have data here through 2009, but we kept them in compliance until through 2012, at which point they removed the system and put in a different type of technology that they wanted to evaluate. But we kept them in compliance the whole time, and you see the range of percent reductions here in red font as well. They were so pleased with how it worked, they actually have trained other municipalities in Tennessee on how to use this type of practice for MS4 stormwater permit compliance. So you're kind of getting the idea here that compost can be used in a wide variety of applications, from as part of a green roof media, as part of a rain garden or bioretention media, using it to reduce runoff in the form of what we call a stormwater blanket, engineering soils, using it in bioswales, even green paver systems where you're vegetating those pavement systems, and of course utilizing or restoring native or natural vegetation or adapted vegetation into these sites. So when you're incorporating all these into a single site or even a watershed, really not only leads to a large effect on reducing stormwater volume and reducing peak flow rates, but also maximum pollutant load reduction as well, and that's really what we're going for here. But it's one thing to conceptualize it, it's another thing to actually see it in action. So I want to share with you, this is a LEED Platinum project, one of the first LEED Platinum projects in the state of Georgia. In 2009 with the South Face Energy Institute, added on to their existing office structure in Midtown Atlanta, which is really adjacent to downtown Atlanta, which you see here in the photograph. They added on their new eco office, and it's the more modern looking structure here in the upper right hand photograph. A lot of stuff going on here related to LEED and green building. This is a green building nonprofit that's actually been around for about 35 years, and they're probably, if not the leading, one of the leading green building nonprofits in the southern United States for education, training, research. A lot of people funnel through here and learn about green building aspects. In fact, they've created their own residential green building program called Earthcraft House, which some of you may be familiar with. But we're here to talk about green infrastructure, not necessarily LEED, and green building. But what they did in their redevelopment and development of their eco office here in the middle of downtown Atlanta is they used green infrastructure practices exclusively, and nearly all of them used compost. And you see a lot of them here in the photographs, from a green roof system to a bioswale system. You see porous pavement there, but that didn't use compost. That's the only one that really didn't. You see compost socks being used to build up the walls of the bioswale, as well as a bioretention system as well. We actually use compost blankets for not only erosion control, but also reduction of stormwater and maximum rainfall absorption around the site. We used a compost-based bioretention media, which you see here in the lower right-hand corner. One thing that's unique about that is not only are we using compost in the media, but there's a cistern down below, so the stormwater actually gets naturally filtered and then captured in the cistern, and they reuse that back up into the landscape and for non-potable water uses within the building. So because of this, they're actually able to capture 100% of the rainfall that falls on the site, even on the rooftops, and stormwater generated. So this is actually a zero discharge facility in the middle of really downtown or midtown Atlanta, Georgia. Because they are reusing a lot of the water that they capture, they're reducing their water consumption by about 130,000 gallons per year, which is equivalent to about 84% of their annual water usage. So this has really become a poster child for stormwater capture and green infrastructure and reuse really in Atlanta and Metro Atlanta. Unless you're part of a workshop or a training exercise like we are today, you don't realize that this is almost exclusively compost-based green infrastructure, and really what you see now, and this is what it looks like with all the vegetation grown in, is really just a high-functioning green infrastructure or low-impact development landscape in the middle of an urban environment. And actually a lot of people come here to get out of their office and eat their lunch in the middle of the day, believe it or not. And to wrap up, if you're interested in more detail of a lot of these practices that I've mentioned, Forrester Media, who publishes Stormwater Magazine, Erosion Control Magazine, they do some other design manuals in this area as well. They've published the Sustainable Site, the design manual for green infrastructure and low-impact development, and they have all 24 of these practices that I've mentioned and really specific details on where to use it, how to use it, when to use it, where not to use it, any existing performance research related to it, how to design with it, how to install it, how to inspect it, how to maintain it, really all the details that you need from start to finish if you want to use any of these practices, both in construction activity or post-construction. And with that, we've used up the better part of the hour, but I think we still can have time for a little Q&A here. I appreciate your time and attention, and we can open it up to questions.
Thank you, Brett. We do have one question. With regard to your slide about off-site conveyance, what kind of conveyance were you talking about? One of the attendees said they don't understand how the carbon is increased by using a ditch or pipe, and they prefer not to ask verbally. So if it's not clear, we can have you follow up afterwards. But can you talk a little bit more about the conveyance and how the carbon was increased, or clarify that for us?
Okay, I'm not sure I understand the question, but how the carbon footprint was increased by discharging into the gray infrastructure. I think that's what they're talking about, but I'm not sure. If it is, I'll answer that. If not, or if I'm not answering it adequately, just contact me afterwards, or you can ask another question. But basically what that's saying is that that water that goes into the gray infrastructure grid has to be treated. And because of that, there's a certain amount of water that has to be treated, and it takes energy to then treat it once it gets to a water or wastewater treatment facility. And that can be either through the initial conveyance system, or even if it goes into a surface water body, at some point somebody's probably going to treat that water again before they use it if it's leading to poor water quality. And of course, anytime we expend energy to treat water, that increases carbon emissions, unless you're working off some sort of energy treatment system that utilizes probably wind or solar, which there are very few of those. So that's where that's coming from. So anytime we have to treat water because there's an increased amount of pollutant or pollutants in it, or increased volume that needs to be treated, we're actually expending energy, and therefore we're increasing carbon footprint. So just by using green infrastructure actually and decreasing stormwater, you're actually reducing carbon footprint and conserving energy. It's just people don't talk about a lot, but it's actually true.
Thank you. And they indicated offline here that you did indeed answer their question, so thank you. Okay. We have another question. How does the effectiveness of the additives vary over time?
Excellent question. We've done longevity studies with the ARS over 25 runoff events, and we found that really for all of these that they consistently keep the same removal efficiencies over 25 runoff events. We didn't go farther than that. We assume that at some point there will be some diminished capacity as well. We haven't reached the point where that was, at least in the study. I do know that if you're including vegetation, you can actually increase the longevity as well, because presumably you're not only trapping more, but these plants through phytoremediation can take up a lot of the pollutants that you're then trapping, then giving the media the ability to continue to do its work. If you're not including vegetation, a lot of folks for stormwater compliance will just use these as kind of cartridges, and in those aspects we're basically doing periodic rain event, storm event testing, so we really know exactly when they are going to need to be replaced as quote-unquote a bit of a cartridge. So.
Okay, that looks like our last question. If there are any other questions from the audience, please raise your hand, and we'll go ahead and turn on your microphone so you can ask that verbally. In the meantime, let me just give a little housekeeping information, and we'll turn it back over to Britt for closing remarks. I want to remind you all who have attended today that I will be sending you a certificate of attendance, which you can use to claim 1 PDH credit from your various professional organizations. We do make the slide deck and the recorded webinar available to you at filtrexx.com/webinars. So if you should need additional proof to show what the content of today's broadcast was, you can use those tools to present for your credit. I also want to let you know that we have some upcoming webinars that you may also be interested in. Since you're here today listening to our topic on low-impact development, you may likely be very interested in tomorrow's webinar on living walls. Our Director of Living Walls Division will give a really great webinar on the different MSE wall systems that Filtrexx offers using these same principles and our knowledge of soils and compost to create effective living structures. We also, that's tomorrow. You can register at filtrexx.com/webinars. You'll also see upcoming on February 11th, excuse me, we have sediment control. On March 5th, another segment of living walls. And on March 11th, pollutant removal. So please do attend any or all of those webinars if you are interested. And with that, Britt, I turn it back over to you if there's anything else you would like to say to our audience before we conclude the broadcast.
No, nothing further. Just appreciate everybody for tuning in. And again, if you have any questions, there's my information. You can contact me offline, and hopefully we'll have you join us again on the next one. Thank you.
Thanks for coming, everybody. We appreciate your time and your interest, and we hope to see you at future webinars. This concludes today's broadcast. Have a great day.